And let me get back a bit about quantum programming model. So we have like a QRAM model, quantum random access machine model, which was defined for the purpose of conventions for writing quantum pseudocode. It starts at like, okay, exactly 30 years ago by Neil, very close by at NIST, right? And I would say afterwards there are some there are a lot of interest in defining quantum programming language, like QCL, QGCL, sorry, and QCL and QPL, scaffold and Kuiper. You can see we have some like okay, PLDI paper. So PLDI is was playing friendly to the quantum, right? Okay. And let me also say something like Prakash and Mingshen case is called quantum wire language. They want to define something called quantum Hall logic. So the language is defined as, okay, you have skip, you have initialization, you have unitary, you have composition, you have measurement, you have while, refers to your question. So the triple they defined is like just a quantum, Hall triple is ACB, right? Here, they want to say that for every input state, which is generally 2 to the n times 2 to the n matrix, satisfies some like a positivity property. So this is the triple is valid. They say like if trace A row smaller than trace B C row, it refers to the output of the state. Okay, so trace is this is just a matrix multiplication. So you see that, and the trace just count the summation of the diagonal entries. And implicitly, you can see that this trace A row and trace BC row must be real number for being able to comparable. Okay. Super nice because it's quantitative, because it's able to track probability. You have inequality. Quantum computation, usually the advantage are not deterministic. Most quantum algorithms, let's say, has some probabilistic advantage. So you want to be able to reason about probability. On the other hand, the Hall triple defined is for the purpose of using classical computer to reason, right? And there are different reasons. You can say that, okay, current quantum computer is not very reliable, always have noise. On the other hand, like we're very familiar with the classical computer to do reasoning. This is our machine now, right? So the idea is, the reasoning usually is about, you can do like a different kind of reasoning, but one question you might be interested is like, we're given the circuits, use a classical computer to compute A from B. You're given B, you want to compute some good A, or you're given A, you want to compute some good B, right? This was never a problem in Mingshen's Hall logic. So let me take, I think I have enough time, so I want to go back here. You can see their first law. They are freely using matrix multiplication, even if it's very large, right? Our observation, or our point is like the matrices are too large to scale within classical computer. 2 to the n times 2 to the n. So we are in a very awkward situation about quantum advantage because let's say reasoning is essential for validating quantum advantage because like we can easily make mistakes because of superposition counterintuitive quantum features. But on the other hand, if we are not reasoning, our program are very likely does not provide us any advantage. So we need reasoning. But if we use exponential cost reasoning, would erase all the advantage. Okay. So let's clearly see that we are facing a scalability challenge. It's like we need trackable predicates, quantitative ones, right? So what property do we care? This is the question. And how do we choose them? Let me start from my previous paper with Jens, is quantum abstract interpretation. That's the motivation. So for quantum state rho and the qubit sets S, qubit sets S meaning let's assume rho is consisting of qubits from 1 to n, and S maybe like 1 to 3 or something. So rho S we denote it as a reduced density matrix. Bear with me 1 minute, I'll explain. So we want to be able to track a tuple of local reduced density matrices, and we use approximation. We use approximation of each reduced density matrix by a projection to track the system. So what is reduced density matrix? You can consider like a classical counterpart is like we have a very large, let's say 1,000 random bits, maybe correlated. And the classical analog of reduced density matrix is marginal distributions. You have 1,000 random bits, highly correlated, and I only care about 1, 2, 3. What's the marginal distribution, right? And the approximation, each reduced density matrix by projection is like we approximate each marginal by its support. Let's say you have a distribution, 3 bits distribution, with half probability all 0, half probability all 1. Now I only care about all 0 or 1. I don't care about whether it's half or something. That's an approximation, right? I was extremely satisfied when we had this paper because, that was my passion then. But then Jens kept asking a question: can we do better? What do we miss? So this is qualitative, which only being able to answer yes or no. And it cannot track probability. Okay, so now we have like 2 tools together, right? We have quantum Hall triple, quantum Hall logic, and quantum abstract interpretation. And for quantum Hall triple, it's ACB, right? I restate everything here. And quantum Hall logic, so it studies general predicates like AB between 0 and 1. Between 0 and 1, you can say the matrix version, 2 to the n times 2 to the matrix version. Extremely bad, but it's quantitative, super good. So for quantum abstract interpretation, it's local projection, scalable, very good, but it's quantitative, only being able to answer yes or no. So we want them to be able to marry. Oh, sorry, let me say one more words. So you can see the way that they are, the QHL is being able to track probability is like A and B is between 0 and 1. Anything between 0 and 1 is continuous. So we are able to track continuous objects. Second time. So then we provide something called local observable. So we do care about the tuples. So we have AS1 to ASM, or we have BS1 to BSM, right? You can see that each S1 or to SM, they only care about marginals, quantum marginals or reduced density matrices. So as long as we not choose this size of SI too big or this M too, if size of MI is not too big, or size of SI is not too big, then the whole number M cannot be too big, let's say, right? So generally, we are able to be, say, doing something like efficient representation like quantum abstract interpretation, but not like a QHL, right? And we also being able to do quantitative reasoning like a quantum Hall logic, but not like a quantum abstract interpretation. We still use this like version, like a trace A row smaller than trace BC row, okay? So the judgment now becomes, this A is defined in this linear combination way of ASI, and B is also defined in the linear combination way of SI. To support my argument, we can easily compute to see that trace A rho in this version would mean only depends on rho S1, rho S2, rho Sn, only depends on the tuple of quantum marginals. And so does B sigma. Seems good enough, right? Now we focus on quantum circuits with only 1 or 2 qubit unitary gates, and we would borrow or like just use the rule of quantum Hall logic is like this. ACB is equivalent, or like this rule is like if A is smaller than U dagger BU. This is a matrix inequality. So the rule is QHL rule. So only the shape of A and B is restricted. We no longer care about arbitrary A and B. We care about this class of A and B. This provides us scalability. Seems good enough, right? But I need to spend the next 5 minutes. So very simple example, let's say we have a C0 gate. If you remember, like the C0 is a black dot and the square plus. Oh no, the circle plus is like if the first qubit Q1 is 0, it does nothing. If it's 1, it does not on the second bit, right? So simple. So you can clearly see that if with the input 0, 0, because the C0 would not apply. Because the first bit is 0, it would not apply the NOT gate on the second bit. Very sadly, the logic or like the rule itself cannot help to prove this thing. Even if we have like an exponential, even if we allow arbitrary computational power. The statement is just cannot support us to prove that, okay, if your input is all 0, your output is also all 0. Or some inequality like that. Moreover, like we're not even able to prove very, very simple thing for this extremely simple example. So the question comes from, for all input, this is extremely strong because most quantum algorithm has a fixed input or 0. So this is the true marriage between QHL and QAI. So you can see the judgment type comes from the QHL and QAI, makes us to restrict the shape of A and B. But we also need the quantum abstract interpolation, P and Q, as a support to say this inequality, I only care this inequality to be valid. This inequality to be valid when the state is in this shape. Right? So this says like if your input satisfies this P, and then your output will satisfy Q, and also you have this inequality. Okay, this is the logic. And you can see no magic, no magic, no magic. The key part is 1, and 2 is kind of reuse of 1. Right? So the workflow is like this. Okay, for given specification or precondition of circuit and circuits, we choose the domain first, S1 to Sm. We approximate the given predicates by the shape predicates, and we apply the rules to try to get something. Okay. Now we are able to prove anything of this C0 without using too much efforts. And we are able to reason about these GHZ circuits. We're able to say like the output would satisfy this form, and this 1 over square 2 was never being able to obtain using QAI. But with this quantitative, we are able to get this 1 over square 2, but we're still missing the phase factor. So this is way beyond, this circuit also way beyond the simulation of unitary. And we could also do like a quantum phase estimation. Okay? So there are some future works possibilities, like we can care about more circuit families, we can do programs with measurements and classical control, and we can mechanize proof search, and we would like to pursue with like this mechanized proof search and integration with symbolic tools like VYZX and VOQC. So Robert will talk about this one. I think I'm right on time. Thank you very much for your attention.
All right. So now we'll take questions. Just raise your hand and I will pass the mic around.
Hi, so please correct me if I'm wrong. I would love to know what all symbolic operators can you then support? Like you talked about like identities being like sort of supported directly, allowing you to have like this scalable verification possible, but is a way to then like handle any kind of control on an operation where you have some outer product for some control value or something like that.
Can you say it again? From the very first sentence.
Oh, I was saying like, can you what all like symbolic operators, etc., can you sort of express? So for having like scalable verification here.
So you're not asking for this future work. It's about our.
I'm like saying like what could happen there is I think my question.
You want to see what could happen there?
Yeah. What all options do you think could be pursued with symbolic tools?
I don't know. I think maybe after Robert's talk, I would have clear idea.
That makes sense.
Thanks.
Any other questions? All right, we'll do one more, and then we'll go to the next talk.
Thank you for the great talk. I wonder if I use this tool, then I wonder if I can check the like BQP algorithm is really BQP or not.
You want a BQP algorithm?
That is.
Right. You want to be able to verify BQP algorithm, right?
Yeah.
No. So there's a hardness result to say like even if you only want to track a single qubit output precisely or with very high precision, you would go beyond to you wouldn't. This question is QSZK complete, quantum zero knowledge complete, quantum zero knowledge proof complete, and so you need to sacrifice some like precision. But if you care about shallow circuits, you can refer to our work with like Tom on Uppsala 200 last year, which says like for any shallow circuit, you can do things completely without any gap and very precise. Yeah, so maybe you want to restrict your computation with some subclass.